Welcome guys. Yeah, this is my mathematical analysis. Yeah, so in this video, we talk about series. Yeah, so previously we talked about series, but now we need to talk about I should say what? Sorry. Previously we talked about sequence, right? So this we should talk about series. Okay. Yeah, so previous data, we already have a notion of what an converge to a. What this means, right? This means that for epsilon greater than 0, you can find integer n such that when n greater than n, such that an minus some point a is less than epsilon, right? And in a general matrix space, we just change the definition to be this. Yeah, so this is the convergence, and then we talk about in the compact sets. I mean, you have subsequence and upper limit, lower limit. Yeah, so in this we talk about another topic, which is about series. Okay, yeah, hope you guys subscribe to my channel. And also most of them follow the Rudin and Apostle. Okay, so just my own notes. Yeah, so definition. Let's define so you get A1, A2 up to A infinity, right? So we can define a series. So let me define let's say SK to be sum of n from 1 to k. Okay, so this is called partial sum. Okay, so my definition is that definition means so people say that if an from n to 1 to infinity converge, means that sk converge to s for k approach to infinity. So basically, partial sum converge, people call this series converge. So when people say that this series converge means that the partial sum converge as the general sequence. Okay, so this is a sequence. This is a series. Okay, so nothing special, right? It's definition. Okay. Okay, so theorem. So if n from 1 to infinity converge, so remember that you need to think about the partial sum converge. Okay, as a sequence. So theorem says if this converge, and if only for epsilon greater than 0, you can find the integer n, right, such that when n greater than n, your a. So you start from, let's say you start from ak, k from n to m, that's all equal to epsilon. Yeah, so basically it should be this. So you can find n such that whenever a greater or equal to n, whenever m and n greater or equal to this n, then you get this k from n to m less than or equal to epsilon. Yeah, so I think the proof is easy, right? So proof, maybe see this, right? So from this right, so what we are saying is that the partial sum converge, right? So let's say define sk to be maybe Sn to be a and n from maybe a k, right? K from 1 to n, right? So Sn converge to S, right? So that's means that Sn is cosy, right? So we already proved it's cosy. So it means that for epsilon greater than 0, there's a n, right? So there's a n, right? So when m and n greater than n, then there's difference, right? So basically the S n minus this S and difference will less than epsilon, right? But by definition, it's just the partial sum, right? So it's ak k from this is n. Actually, wherever, right, there's an absolute value, and so the difference basically just a k from it's n plus 1 to m. Right, you can shift this, you just shift it a little bit, and you get this, right? So this direction is trivial. Okay. And okay, so how about the converse, right? So how about the converse? So converse, so now for epsilon you can find n, right, such that m greater or equal to n, that's it. So what this means that this is just s right? S and you can write it as m minus, let's say maybe m plus n minus 1, right? So from this, just tell you that this sk and it's cosine, right? So in our setting now, actually I haven't not say yet, but in our setting this this series, right, is basically by default is in the Euclidean dimension Rk, right? So now it's cozy, and also plus this Rk is complete space, right? So complete means that every cozy sequence converge, right? So this is cozy, so it implies converge. Okay, so particular, right? So our theorem says what? M greater than n, right? Your sum from n to m, right, should be less or something, right? So you can pick m equals to n, should be okay. So you can pick m equals to n, which just tell you that an less than epsilon, right? So for n large enough. Okay, so from this you pick a theorem says that if an converge, yeah, this is probably the most simplest theorem. So if an converge, sum of an converge, easily from this say that an goes to 0 as n goes to infinity. Okay, so this is the necessary condition, right? So if you see some series which when it goes to infinity, which is non-zero, means that it will not converge. Woo. Okay, so but let's notice that the converse is not true. It's converse is not true. Okay, so famous example is harmonic series, right? So diverge, and then you can use your calculus to prove it's basically up to log n. Plus this is Euler-Mascherani constant. Who knows, right? So just tell you that so your 1 over n goes to 0 as n goes to infinity, but this guy still diverge. So which tell you that the converse of this statement is not true. Oh, okay. So let's see what's the next topic. Okay, so we keep going some theorem. So A is that if an absolute value less than Cn for SA n greater or equal to n0, then if sigma Cn converge, then sigma An converge. Okay, yeah, so this is basically the so-called comparison test, right? So basically, if you find something from this guy absolute value is bounded by other guy, and this other guy converge, you converge. Okay. Also B is that n greater or equal to dn greater or equal to 0, right? So if let's say for n greater or equal to n0, then if sigma dn diverge means that this guy is already so big, right? So then an diverge. This is basically the comparison test. Okay, so I think this is a simple. I mean, your intuition is correct, right? Because I think these two are very intuitive. But the proof is also simple. Okay, so let's see. So the proof. So for epsilon greater than 0, right? You can find n greater than n0 large n such that your m sorry, this is this. Basically, your m n greater or equal to n greater or equal to 0. By definition, right? You will have ck from n to m, which is converge, right? Okay, so you take absolute value, right? So you get this because this guy is positive, right? So we take absolute value, right? And this is positive, right? So this is just this. And greater or equal to sigma ak, right? Because ak is less than absolute ak is less than ck, so it's k from let's say n to m, right? So that's equal to epsilon, right? So you get k from n to m, which is less or equal to epsilon, which tell you the sum of an converge, right? And notice that the an is less or equal to an absolute and then minus an absolute, right? So once you prove these converge, then easy to show that these converge. Okay, so the same reason you can just use this definition. Okay. Yeah, so we prove A. Okay, so B is simple, right? Because you know that the sigma n from 1 to infinity, right? So for each partial sum k greater or equal to d and n from 1 to k, right? So then this diverge. So easy to show that this diverge. Actually, you might think that I didn't prove anything, right? But actually I proved. Yeah, so you can think about it. Right? Because I mean, or you can prove by contradiction, right? Suppose these guys converge. So it means when k goes to infinity, this guy will bound it by something, right? Will approach to something. But this guy already diverge, right? And then the key step is that this is infinity, right? So the only way it diverges, it goes to infinity. So infinity will less than some fixed number, which is a contradiction. So once these diverge, then this will diverge. Okay. Okay, I think maybe in the next time we talk about some examples. Let's see how many pages I talk about. Okay, I think it's enough for today. See you guys next videos.